In this table, you have the simulated data that you're using to prepare your report. You're given the metal that you have in the cathode, the metal that you have in the electrode, that is the anode, and then the experimental value or the measurement that you're taking for each of these spontaneous galvanic cells. So I'm going to show you how to complete the calculations for this experiment. I'm giving you just two examples, and with those two examples, we're working the numbers that are missing in the table and also the reactions that you have to complete. So the first thing that you have to find out is the potentials for your half reactions. So in the table we have, I am writing numbers. Number 1 corresponds to what you have as the measured cell potential or the experimental number. Number 2, this is the cell potential that corresponds to the reaction that is happening in the cathode where the reduction is happening. In number 3, you have the cell potential for the half reaction that is happening in the anode, which is where the oxidation is happening. And then I have labeled here as number 4, that's the calculated cell potential, which is what you have to find out. And then here at the end of your table, you need to calculate the percent error, which is what you're doing when comparing your calculated cell potential, which is in theory what you should be getting, and the measured cell potential, which is your experimental data. So to find out the potentials for your half reactions, we're using the table that you have in the lab manual. This is a simplified table, but it's the same thing that you have. So I'm going to look at the table and I'm going to find out the potentials for the reactions that I'm looking at. So for my galvanic cell number 10, I have copper and zinc. So copper is down here, and then zinc is over here. So you can look at which metal you have in the cathode to identify the number that you need here for your cathode, and which metal you have in the anode to find out what number you need here in number 3 for the anode. The numbers, you're arranging them in a way that you will get a positive potential, cell potential for a spontaneous cell. So your equation is cathode minus anode. So you're arranging your potentials here to get a positive number from that subtraction. If you do negative 0.76 minus 0.34, you will get a negative number. So that does not correspond to what you have here in the table. To get a positive potential, the zinc is being oxidized, and that's why you have zinc here in the anode and copper here in the cathode. So if copper is in the cathode, the potential that goes in this table here for the cathode will be the one that you have for copper, which is 0.34. And then your electrode in the oxidation part of your electrochemical cell is zinc. That's the anode, and the potential that you need here is the one that corresponds for zinc, and that number is your 0.76. So to calculate the cell potential, you're using the subtraction. So you have the cathode potential minus the number that you have for the anode. And that's for your number 10, cell number 10. So that will be 0.34 minus. So that's the calculated cell potential. So for number 11, we have silver in the cathode. So I have my potential for silver right here in the cathode. And then zinc, it's in the anode again, so that's the same one, 0.76. So you calculate your cell potential, standard cell potential, 0.80 minus 76. So you have the cell potential for your galvanic cell number 10 and galvanic cell number 11. Now to calculate the percent error, what you're doing is the number 4, which is your theoretical value, right, minus what you have in number 1, which is the experimental value, divided by your theoretical value again times 100. Whatever number you're getting, it has to be a positive number because this is the absolute value of your number. Besides completing the table, you have to do something else. We have to write out the balanced chemical equations, right? And well, you calculated the percent error. So to write down your balanced chemical equations, I'm not asking for all 21. I'm asking for the ones that I'm listing here. And I'm going to give you the examples with electrochemical cell number 10 and 11 again. So in number 10, we have copper and zinc. So copper is the one that is being reduced. You have that one in the cathode. And zinc is the one that is being oxidized. You have that one in the anode. So those are your two metals. So you can find the half reactions for the reduction potentials in the table. I'm writing exactly the same equation that you have in the table for copper plus 2 being reduced to copper 0. Copper plus 2, it's gaining 2 electrons. That's what reduction means, gaining electrons to become copper 0. Remember, you have two positive charges. Copper plus 2 with 2 positive charges is gaining 2 electrons. That's 2 negative charges. So your 2 positive charges are being cancelled by those 2 negative charges, and that's why it goes to copper 0, no charge or neutral. So that's what's happening in the cathode, right? Now in the anode, you have zinc. The equation from the table that corresponds to the reduction, because those are for reduction potentials, is that equation. That equation represents the reduction of zinc, but in your electrochemical cell, zinc is not being reduced, zinc is being oxidized. So for the element that is being oxidized, your half reactions needs to represent an oxidation. That half reaction that I'm writing there, which is just your reduction reaction but flipped, it's representing the oxidation of zinc. You have zinc solid with the same number of protons and electrons. When you have the same number of protons and electrons, you have a neutral charge or no charge at all. That's why you have zinc as a solid, the element. Now, when zinc is being oxidized, you're forming the ion of zinc, losing 2 electrons and those 2 electrons. So zinc solid is becoming zinc plus 2 electrons when zinc solid is being oxidized. So this is the reaction that is happening in the anode. Now you need the overall chemical equation. So I'm going to write down my reaction for the reduction here, which is the one that you have for copper. And right under that one, I'm going to write down my reaction for the oxidation of zinc. Okay. So for you to get the overall reaction, you have to add both reactions together. Now, for you to add both reactions together, you need to have the reaction balanced by mass and also by charge. What that means is that if you have 1 mole of copper on the product side, you need to have 1 mole of copper on the reactant side. That's balanced by mass. By charge means that you need to have the same number of electrons on both sides of the reaction. If you look at the reaction for the reduction of copper, you have 2 electrons. So copper plus 2 is gaining 2 electrons to become copper solid. And then for the oxidation, you have zinc solid becoming zinc plus 2 electrons, which means that you have the same number of electrons on both sides of the reaction, and that number will cancel out. You're forming 2 electrons from the oxidation, and you're using 2 electrons in the reduction. That's what that represents. Remember, your electrons are always moving from anode towards cathode. You're forming the electrons in the anode, where I have here my reaction for the oxidation, and those electrons are being used up in the reduction process. So it makes sense not to have overall electrons in your reaction, because the electrons are being transferred, all of them. So once you have your electrons cancel out, you can just add everything that is on the reactant side goes together. So you have copper plus 2 going to copper solid, that one is being reduced, and then you have zinc solid going to zinc plus 2. So for number 11, and now for this one, I'm not writing down everything. For number 11, you have zinc as being oxidized again with your potential of negative 0.76, and you have silver as being reduced, gaining the electrons. Okay? So the equation for the reduction for silver, from the table, you have silver plus 1, gaining 1 electron, becoming silver solid. Now for the oxidation of zinc is the same one that we used before. Zinc solid going to zinc plus 2 electrons. Now, a difference between these reactions, these two reactions here and the previous two, the number of electrons is not the same. You have silver with a charge of plus 1 gaining 1 electron to give you silver solid. And for zinc, you have 2 electrons. So we have to balance the number of electrons. If you have just 1 electron for silver, silver is the one that is being reduced. Every mole of zinc that is being oxidized it's giving you 2 moles, okay, of zinc plus 2. It's giving you 1 mole of zinc plus 2, but 2 electrons. So those 2 electrons, they need to be transferred, both of them. So for you to be able or to have something to accept both electrons, you need to have 2 silver ions. Each one will get 1 electron. So if I multiply my whole reaction there by 2, that will give you 2 . So now your number of electrons is going to cancel out. You see, you're getting 2 electrons from silver, from the oxidation of zinc. And those 2 electrons are being used up for the reduction of silver. But for you to use 2 electrons, you need to have 2 moles of silver ions. So each one will get 1 electron from the zinc. So now you can add your 2 reactions together because you have the same number of electrons. So I'm going to write down my equation here for the reduction of silver. So you see your 2 electrons here are canceling out with 2 electrons there. So whenever you have to balance the number of electrons, you're going to use a coefficient. You're going to multiply the whole half reaction by a number. So you can multiply just one of them. Sometimes you have to multiply both of them. For example, when you have 2 electrons in one reaction, half reaction, and 3 electrons in the other half reaction, your overall number of electrons in that case has to be 6, so they can be canceled out. Okay? So here you have zinc solid plus 2 moles of silver plus 1, going to zinc plus 2 plus 2 moles of silver solid. So this reaction here, it's balanced by mass. You have 1 mole of zinc on each side of the arrow, and you have 2 moles of silver on each side, so it's balanced by mass. And it's balanced by charge because your electrons were canceled out.